All right, perfect. Let's welcome all of the Spotlight speakers sort of collectively as a group.
All right, also collectively as a group, I want to thank all the organizers for putting the event together. I'm very excited about the rest of the week. My name is Quentin Ferry, and I'm going to tell you a short story about abstract world model in transformer models. I don't have a Lego model of a transformer, I'm sorry. So what are abstract world models? Well, our brains, because it needs to predict the consequence of our action, has evolved this very cool trick where it can take partial observation and come up with an internal model that sort of capture the latent blueprint of our reality. Now, this abstract world model that we conceptualize as a collection of abstraction is critical for us to navigate novel situation or generalize. At the same time, deep learning systems have historically struggled with generalization until very recently, where we got a switch from supervised to self-supervised learning and also combined with the expressiveness of the transformer architecture. And that gives us very powerful foundation models that are actually great generalizers. So to me, this raised the question, which is, do those self-supervised transformer network also abstract world models? And if they do, can we go inside those models and try to find this abstract world model and understand how they play into the decision-making of such systems? So to do this, we trained small-scale transformer to reconstruct partially masked visual boards. Importantly, those boards are made by adding to the board some objects that are predefined into a latent blueprint right here. Now, once the network is fully trained, it is able to generalize to board that it has never seen before. What we can do is get inside the model, look at the activation, and try to find representations that capture this latent blueprint that was hidden from the model. When we do this, what we realize is, despite the fact that the model is actually just asked to think at the level of the token in, token out, we find that intermediate representation encode high-level concepts. So just to exemplify this, here, for example, we have two tokens that are perceptually distinct, but belong to the same object. And what we found is that the embedding for those tokens will transiently converge in the middle of the network to a low-dimensional representation that we can decode as meaning object A. And in fact, if we look throughout the network, we find such abstract representation or abstraction for every single aspect of the latent blueprint that I just showed you. So this is an hint that there is some sort of an abstract world model into this system. However, maybe they're just byproduct to the abstraction. So the next step is for us to show that actually those abstractions play a critical role in the computation of those models and also carry the information that we hypothesize they carry. So to do this, we use gain-of-function experiment as the one illustrated on the left here. So imagine I'm the transformer and I have to guess what is the identity of that token in this object A. What's happening is, as the transformer transformed the embedding for that token, it's going to, at some point, encode the abstraction for object A. At this point, I can just stop the network and swap this abstraction for an abstraction of a different object. Now, when I resume the computation of the transformer, what I see is that the transformer does a predictable mistake that shows us that it's actually believing it's reconstructing a different object. Okay? So using the same trick, we can also go further and show that if we have different objects of different complexity, the corresponding abstractions form part-whole hierarchy that map the compositional nature of the latent blueprint. Now, to wrap this up, what we wanted to do is come up with a way to more easily be able to delineate and manipulate those abstractions. So we come up with a novel architecture that we call language enhanced architecture, or LEA, which is designed to force the network into telling us what it's learned through the self-supervised learning process. So we have, in addition to our inference network, a second network whose role it is to take the abstract representation of the first one and convert them into a sentence-like representation. Now, the sentence-like representation, so that it carry meaning, we pass it back through the inference network, and we ask the inference network to be able to reconstruct the full board just from that representation. And what we see after training of this model is that Leah actually develops a language that is geared towards talking about the abstraction that the network secretly learned. And what we're able to do is find a mapping between those abstraction and the linguistic pattern that correspond to them. And once we have this, we can basically force or coerce the inference network into creating whatever output we want. So we see this as a great way to discover what those models learn and also have a way to steer their behavior. So with this, I will just conclude, and I will thank Takashi Kawai and Joshua Ching that helped with this project, and my supervisor, Susumu Tsunegawa. Thanks for your attention.